Okay, Bismillahirrahmanirrahim. Assalamualaikum and a very good morning. Okay, from the lump element analysis earlier, so now we are going to proceed with the analysis of waveguide structure. Okay, for this part one, we are going to focus on two types of waveguide, which are the rectangular and circular. Okay, before we begin, let's recap or let's revise the brief introduction onto the transmission line and also waveguide structures that you can find from the e-learning. So the first link basically have been uploaded in the e-learning. That include the description and some equations related to the rectangular, coaxial and circular waveguide, while the second one related to the planar waveguide that includes microstripline and stripline waveguide. Okay, this slide summarizes the main differences between the transmission line and also the waveguide structure. Okay, both are waveguide, but one using the transmission line technique and the other one using the waveguide structure. So the first one, in terms of the structure itself, so transmission line has two or more conductors separated by insulating medium or dielectric medium. For example, two parallel wire, coaxial cable, microstrip, and etc. While the waveguide structure typically includes one conductor. So it's either in rectangular shape, circular, or etc. And normal operating mode for the transmission line is TEM mode or quasi-TEM, while the mode of operation for waveguide structures are TE or TM mode, but it cannot support TEM mode. For transmission line, there's no cutoff frequency for the TEM mode, while for the waveguide, it must operate. The waveguide must be operated at a frequency above the respective TE or TM cutoff frequency mode to make sure it is propagated by using the specified TE or TM mode. So in this case, the waveguide F must be higher than the cutoff frequency. Okay, another one for the transmission line, there will be significant signal attenuation at higher frequencies due to conductor and dielectric losses, while for waveguide, lower signal attenuation at higher frequencies if compared to the transmission line. Okay, let's continue with the rectangular waveguide analysis. Okay, some revision on rectangular waveguide. You can see this from the brief introduction on waveguide structure. Alright, so basically for rectangular waveguide, the dimension will be A times B. So A is the longest dimension or the width of the structure if the A is larger than B, while for a square waveguide, A will be equal to B. Alright, so the dominant mode will be 1, 0, and the TE10 will be basically showing that there will be transverse electric mode, in which if one here representing only one half wavelength across the width of the structure. Okay, so the signal or the wave will be propagated in zigzag motion inside the structure, okay, and it will be reflected by the wall of the rectangular waveguide. Okay, so the conduction of energy in waveguide through the dielectric within the waveguide, and it will be reflected at the edge of the inside of or the wall inside the waveguide itself. And usually the waveguide is separated by air. Okay, let's look at how the signal propagates inside the waveguide. So in waveguide, wave velocity varies with frequency. Okay, so we'll see different mode for different frequencies as well. Right, there are two types of velocity: phase velocity and group velocity. So for group velocity, it's defined the velocity at which a wave propagates within the structure, and it's given by capital Vg. Okay, the G stands for group, V velocity, which can be calculated by c squared over Bp. Vpp here is phase velocity, and it can also be calculated by using this. Alright, lambda naught is the free space wavelength, while lambda c is the cutoff frequency wavelength of the structure. Alright, so this is group velocity, phase velocity, and c is the speed of light. Okay, while the phase velocity, the velocity at which the wave changes its phase. Alright, so the phase velocity can be calculated by using this equation. So it still relates with the speed of light, the lambda naught, and also lambda c. Okay, so what's the difference between f naught and lambda naught? So lambda naught is the wavelength, while f naught is the free space resonance or operating frequency. Okay, inside the waveguide, the wave propagated in zigzag manner. Okay, just like this illustration. So how the signals being propagated in zigzag motion, where there will be a reflection at the edge or inside the wall of the waveguide structure. And the electric field maximum in center and zero at surface of the wall. Okay, so we can see that from the electric field distribution or the wave distribution, we can see that the maximum, okay, the red color indicates the maximum field, okay, while you can see that the blue basically representing the minimum, okay, the least field which exists closest to the wall. Okay, the blue lines basically appears here, while the red fields distribution we can see higher at the center. Right, so the wave cannot travel straight down a waveguide due to the reflection at the wall, and electric field exists next to the conductor will be short circuited by the walls. That's why we can see that very minimum field distribution besides the wall. Alright, in terms of the phase velocity and also the group velocity, it's basically in perpendicular to each other. So Vg, group velocity, the direction of the propagation, while Vn is basically the normal velocity, okay, where it is perpendicular to the Vg. Okay, rectangular waveguide mode of operation. So we have discussed this earlier. So, and the TE10 is basically the dominant mode for a rectangular waveguide. So just a quick overview on the mode of operation for a rectangular waveguide. So the wave travels down the waveguide in different configuration called propagation mode. So it's being represented by the MN. Alright, either it is TE or TM modes, okay, transverse electric or transverse magnetic. So what does TE means and TM means? So you can just read through this statement. And the mode of operation, again, as mentioned, define whether it is TE or TM and the mode's number. So M basically number of half wavelength across a waveguide with A. Alright, so this is the width A. So number of half wavelength. Okay, for example, TE10, we know that the M is 1. So only one half wavelength appears across the A or across the width of the structure, while the N number of half wavelength across height B. Okay, height B. Okay, the slide summarizes the field distribution for different TEM mode for a rectangular waveguide. So you can see at different cross section, for example, number 1, when you cut it here in the middle and you view it from top, okay, and the second one when you view it from here, okay, and then number 3 when you cut it in the middle and you view that from here. Okay, so different cross section, you will see different field distribution, okay, different shape of field distribution depending on the modes of propagation. Okay, next, the waveguide have a minimum frequency called cutoff frequency, FC. So for a field waveguide, the relationship between the guide wavelength and cutoff frequency is as shown. The lambda g representing the guide wavelength. Okay, c is the speed of light. For a field waveguide, if you have different medium in between the metallic wall, therefore the c will be different, okay, depending on the permittivity of the materials, and also the mu, the permeability. All right, and the cutoff frequency is the lowest frequency that the wave can propagate within the waveguide. All right, so the FC will be depending on the modes as well. All right, for M and N, so the FC can be calculated by considering the modes number and the cutoff wavelength related to FC as well. So you know that lambda equal to C over F. So lambda C will be equal to C over FC, which it will depend on the modes number M and N, also and the structure dimension A and B. And remember, for a rectangular waveguide, A is the longest width, okay, and B is the height. And the dominant mode for a rectangular waveguide is TE10. It is a natural mode. Waveguide may act as high pass filter that pass only frequencies above cutoff frequency, so F larger than FC, to ensure that the wave is propagated by using the specified TE or TM mode. And a rectangular waveguide normally operate within frequency between FC and 2FC, as long as it is higher than the FC and 2FC. Okay, higher modes is undesirable because they cannot couple well to load and cause higher reflections. Okay, the slide summarizes the important equations related to the rectangular waveguide. So you don't have to memorize all this because all the equations will be provided to you during the test or exam. Okay, just you need to familiarize yourself with all the parameters involved. For example, what is A and B, and what is M and what is C. Okay, what will be beta, and VP representing what, and etc. Okay, and another one is this one, the intrinsic impedance. It can be calculated by 120 times pi. Okay, let's look at an example. A rectangular waveguide, dimension of 5.1 cm by 2.4 cm. So that's a rectangular waveguide. So the longest dimension will be your A equal to 5.1 cm and also B equal to 2.4 cm. Okay, when you have a question, I will recommend you to draw or sketch the waveguide structure so that we can see, you can relate the parameters with the illustration. Okay, and then calculate the cutoff frequency of the dominant mode. Alright, dominant mode here, obviously for a waveguide structure, rectangular waveguide, the dominant mode will be TE10. So you know your M will be 1 and your N will be 0. So to calculate the cutoff frequency, so you can refer to the equations from the table or from the appendices. Right, so the FC will be equal to C over 2 M over A squared plus N over B squared and square root. So as usual, I would recommend you to write down the general equation before you include in any values in your calculation. So C is speed of light, 3 times 10 to the power of 8 divided by 2, and then square root of your M equal to 1 divided by your A is 5.1, and don't forget it is in cm, so please make sure you use the SI unit, the standard unit. So times 10 to the power of minus 2 and plus N equal to 0. Since it is 0, so you can just ignore this one. So your FC, you should get it 2.94 gigahertz. Okay, please make sure you complete the calculation and check properly. Okay, let's look at the second example. A 6 gigahertz wave is propagated in a 3 times 1.5 cm waveguide. Right, so calculate the followings. So again, you have a rectangular waveguide with a dimension of 3 times A equal to 3, the unit is cm, and times B equal to 1.5 cm as well. Calculate the cutoff frequency, cutoff wavelength is the lambda c. The guide wavelength is the lambda g. And the group and phase velocity, the v, g, and also vp. And the characteristic impedance z, te or tm. So in this case, for a rectangular waveguide, the dominant mode, we can assume it is in dominant mode, right? Since the first question also related to dominant mode, so ZTE Mn equal to 10. Okay, let's calculate the first one, the cutoff wavelength. Okay, the lambda c, right? Please refer to the appendices or the table. Make sure you choose the correct equation and write down the general equation before you solve them. Right? So cutoff wavelength represented by lambda c equal to 2 divided by the square root of m over a squared plus n over b squared. For dominant mode, so you know that TE10, in which M equal to 1, N equal to 0. So in the given question, you have a structure with your A equal to 3 cm times, B equal to 1.5 cm. Okay, so now once you have the general equation, then you can include all the values into your equation. So M equal to 1 over A, 3 cm, 3 times 10 to the power of minus 2 squared plus, I would say 0 because N equal to 0, square root. So you should get your lambda C equal to 0.06 meter. Okay, next, the guide wavelength in dominant mode as well. So refer to the equation. So lambda g equal to c over f squared minus fc squared square root, or this one equal to lambda naught divided by 1 minus lambda naught divided by lambda c. So you can choose to solve by using either one, okay, which one easier to you, right? But I would say that in this case, since we already have the lambda c, so you can straight away use this equation. You can straight away use this one since you already calculated the lambda c from the first question, but you don't know yet the lambda naught. So lambda naught equal to c over f. So what is your f? F given from the question is 6 gigahertz. Okay, so c 3 times 10 to the power of 8 divided by 6 gigahertz. Alright, so once you have the lambda naught, then you can calculate your lambda g. So your lambda g should be equal to 0.09 meter. Okay, next question C. Please write down the sub-question number, the group and phase velocity. So Vg from the table, the equation will be c squared over Vp. So you don't know yet, you are yet to know the Vp, so you can use the second equation, c multiplied by 1 minus lambda naught over lambda c squared. Right, so c the speed of light, lambda naught you have calculated that from question B, c over f. Lambda c you have calculated in A, so you can get the Vg straight away. Right, for Vp, same steps. So Vp equal to c over the square root of 1 minus lambda naught over lambda c squared. So the difference between Vg and Vp, this one multiplied by c, and this one divided by this group. Okay, so you know the lambda naught and you know the lambda c, so you can get the Vp straight away equal to this. Okay, lastly, the ZTE, the characteristic impedance at dominant mode ZTE. So ZTE equal to intrinsic impedance divided by 1 minus lambda naught divided by lambda c squared and square root. So what is the intrinsic impedance? So the intrinsic impedance can be easily calculated by 120 pi, and the rest are the same as earlier. So finally you can get your ZTE equal to 682 ohm. Okay, we have another example. So we have discussed 2 examples earlier, so I want you to repeat this example and make sure you try out every single component of the questions. Okay, you need to calculate the cutoff frequency, cutoff wavelength, guide wavelength, lambda g and lambda c, the group and phase velocities Vp and Vg, the characteristic wave impedance, but this time you have 2 different modes. Okay, so the answers are down here, so make sure you write down the complete solution for your future reference. Okay, next we are going to continue with circular waveguide analysis. Okay, for a circular waveguide, so it is as the rectangular waveguide, a hollow structure, round metal pipe that supports TE and TM waveguide modes, and the dominant mode is TE11, and for TM it is TM01. So the modes is defined by nm. If you compare to rectangular, it is TEMN, but for circular waveguide, it is TE or TMNM, right? The order of the subscription, right? So for TE modes, okay, as rectangular, so the wave propagated as in zigzag motion as well, where the wave will be reflected at the edge of the metal wall. All right, the TE modes defined by the cutoff wave number given by K, C, and M that can be calculated or estimated by rho prime and M divided by A. So A is the radius of your circular waveguide. And the propagation constant of the mode is beta and M, can be calculated by using this equation. So K is the wave number, and the cutoff frequency can be calculated by using this equation. So the P and M can be estimated by using the electromagnetic fields derivation. So, but the values can be easily gathered from a mathematical table that will be provided to you for your analysis. Right, so the table below basically represents 3 samples of the rho or P and M values. So the N varies while the M mode presented here. Okay, while the wave impedance is given ZT for TE mode, ZTE equal to the intrinsic impedance K wave number divided by the propagation constant. Okay, while for the TM modes, the propagation constant is given by beta and M. So again, the order of the modes is NM, while the dominant mode or the first mode for TM is 0, 1. TM 01, N equal to 0, M equal to 1. And the propagation constant can be calculated by using this value. And the cutoff frequency FC for that particular modes can be calculated by using this equation. Right, if you compare the TE modes and TM modes, for TE modes, there will be rho prime and M. Okay, but for TM modes, it is just rho or P without the prime. Okay, so make sure you refer to the correct table when you want to analyze the modes, okay, whether TE or TM modes. While the wave impedance for TM modes given by ZTM equal to this following equation. All right, okay, the figure down here just showing the cutoff frequency of TE and TM modes relative to the cutoff frequency of dominant TE11 mode. Okay, this slide basically summarizes the field distribution for a circular waveguide depending on the modes of propagation. All right, so TM01, TE01, TE11, this is the dominant mode. All right, so it depends on the radius of the structure, and also the modes, okay, of propagation, where the E and the H fields basically propagate in perpendicular to each other depending on the modes. It is the modes of operation. Okay, the table summarizes some parameters that you need to consider in your calculation for the cutoff frequency of a circular waveguide. So some of the parameters have been seen earlier in the previous slide. So we have seen the K, the wave number. So the related equation to get the wave number is shown in this table, and the table will be provided to you together with the rho and M and rho prime M N tables for your analysis. Okay, let's look at an example. for a circular waveguide. So the question asks you to find or to calculate the cutoff frequencies of the first two propagating modes, which are the TE11 and TM01 of a Teflon field circular waveguide. So you have a circular waveguide filled by a Teflon material, dielectric material. Okay, here you have Teflon, and the A is given as 0.5 cm. Again, please make sure you consider the unit in your calculation. And given the relative permittivity of the Teflon equal to 2.08, so epsilon r for the Teflon is 2.08. Alright, you can simply calculate the cutoff frequencies for both modes by referring to the equations. So the answer is provided down here. So you just need to familiarize yourself with the parameters involved. So for TE mode, so you need to refer to a rho prime or P prime. So in this case, rho prime and M, and n equal to 1, m equal to 1. So you need to refer to the the table for TE modes to get the rho prime values. So basically at n equal to 1, m equal to 1, so the rho prime is equal to 1.841. We'll refer to the previous slide. There's sample of rho prime and m values. And the epsilon r, or the permittivity of the Teflon, is given as 2.08 from the question. So you can get the frequency, cutoff frequencies for the TE11 mode equal to this. And same steps for the TM01. However, remember that from the basic or the fundamental equation, you need to consider the rho and m. So in this case, n equal to 0 while m equal to 1. So refer to the table, get the rho n equal to 0, m equal to 1 value. So from the table, you should get this value. And the cutoff frequency for TM01 mode equal to 15.92 GHz. Up to now, thank you.